talk about short-term variability with HMI insights into flare magnetism. So whenever you're ready there, Masha, thank you.
Do you see my screen?
Yep, that looks good.
Thank you for inviting me to give this talk. With launch of HMI 10 years ago, we started observing vector magnetic fields in the photosphere on a regular basis. In this beautiful sequence of observations from HMI, we see emergence of fairly large sunspots across the disk during several days. So in this talk, I will overview some aspects of how these measurements helped us improve our understanding of flare magnetism. And I'll only try to answer the 4 questions below, omitting the majority of works done on this, on other topics. So do photospheric magnetic fields change during flares, and how? Can we estimate the amount of magnetic flux reconnecting during flares? Can we estimate the amount of magnetic flux in the erupting structures? And what is the distribution of electric currents? So let's start. The topic that has been already discussed in quite a bit of detail: do magnetic fields in the photosphere change during flares? And before SDO, when we mostly had line-of-sight magnetic field measurements, we learned that indeed there are rapid persistent line-of-sight magnetic field changes. With HMI SDO, we have much higher spatial and temporal coverage of vector magnetic fields. And what we learned is that at the polarity inversion line, over the flare, magnetic field becomes more horizontal, and away from the polarity inversion line, it becomes more vertical. And here is the illustration of my point, a center of the sunspot, and the difference of the horizontal magnetic fields over just 20 minutes in the flare. So what we see here is enhancement of horizontal magnetic field close to the polarity inversion line. This change is quite gradual by over 400 Gauss, and away from the polarity inversion line, on the opposite, we have a decrease of horizontal magnetic field. There have been quite a bit of analysis of this type during last 5 years. And here's another nice paper describing detailed analysis of 15X class flares. So the unique thing about HMI SDO is that it has allowed us to perform statistical studies of magnetic field changes. And here is an illustration for that. A paper by Castellanos-Duran in 2018 analyzed 75 flares larger than M1. And what they found is that these magnetic field changes seem to be quite universal. And in fact, there is this correlation between the Gauss X-ray class and the line of sight change area. So as has been previously mentioned, the general scenario here is magnetic implosion, explaining it. However, I would like to note that recent study by Klein et al. Using ground-based observations found some inconsistencies between photospheric and chromospheric spatial signals. So we need some additional multi-height measurements here to highlight and understand what's really going on. Switching to my second topic, can we estimate the amount of magnetic flux reconnecting during flares? And before I talk about flare ribbons and dimmings, I want to show you this very general solar flare cartoon. What do we think is the standard flare model? A set of sheared magnetic field lines separated by a current sheet here, reconnect in the X point. As a result, we have plasmoid on one side and a set of closed field lines on the other side. At the foot points of this newly reconnected closed loops, we have flare ribbons, which are foot points of exactly newly reconnected magnetic field lines observed in the chromosphere. In the 3D picture, we have something very similar, but a flux stroke here, closed field lines here, ribbons, and then a new thing, dimmings, which are the foot points of expanding coronal structures observed as darkening in the coronal lines. The main reason I'm showing this cartoon here is to illustrate that while we cannot measure the amount of magnetic flux that reconnects in the corona because of the conservation of flux, we could use the flare ribbons to estimate what's the total flux that has been reconnected. And also the same for the dimming. By counting the amount of flux within the darkened area, we could estimate the dimming flux. So again, if we have ribbon and magnetic field measurements, then we can estimate the amount of flux that reconnects into the corona. And here is an example of a flare. Ribbon evolution is a function of time. On the right is the cumulative ribbon mask over the magnetic field. And if we integrate B over the ribbon area, then we get reconnected flux. Summing it up cumulatively as a function of time, we get reconnection flux. And note how nicely balanced the positive and negative fluxes are, meaning that these measurements are not garbage and they actually balance each other quite nicely. So before SDO, aligning ribbons with magnetic field observation and also dimming observation was not easy. So only a few events have been analyzed. With SDO, we're dealing with the first time when both vector magnetograph and ribbon dimming imaging capabilities became available together. So no time-consuming alignment is required. And now is the perfect time to assemble a large database and perform a large statistical analysis of what's actually going on. So one of the papers that described the ribbon database, ribbon properties is the RibbonDB paper by myself and the collaborators, where we analyzed all flares larger than C1 within the 45 degrees from the disk center. Mostly X-class flares shown in blue as a function of time, but also some 300 M-class and almost 20 X-class flares. The RibbonDB information contains the basic flare, start peak times, and also active region magnetic flux and areas and the flare ribbon properties, which is the key here. And if you're interested in the to play with this database, make sure to go to this website here. So what have we learned from the database? Here are the two scatter plots showing flare peak X-ray flux versus active region magnetic flux, something we know very well, and the unsigned reconnection flux, the new thing. So while there is no correlation between the flare peak X-ray flux and the active region flux, there is a very nice correlation between the flare size and the unsigned reconnection flux. This nice power law could be described by the possibly heated flare loops shown in here. Another interesting property is the fraction of flux reconnected. What's the fraction of the active region participating in the reconnection? With RibbonDB, it is easily to be done. And what we find is that there is this interesting correlation. The larger is the flare, the larger is the fraction of the area that participates in the reconnection. And why is that? It's still not entirely clear. Another thing we could look with RibbonDB is what defines the flare duration. Is it the amount of flux that reconnects? And the answer is yes, but wait a minute. Using a study of 50 flares by Toriumi et al., they found a linear relationship between ghost soft X-ray duration shown in here and ribbon separation, flux, and area. So you see that there is this nice scatter plot. And an explanation for this correlation has been suggested the same year by Rip and Toriumi, saying that flare duration is defined by the flare reconnection time related to the alpha in transit time over the reconnected loop length, which in turn is related to the ribbon distance. So everything is nicely explained. However, later in 2019, further analysis was performed using RibbonDB, where they found that this nice correlation is really nice for X-class flares. But as you go to M-class flares, C-class flares, and all-class flares, you see that, that this relationship is gone. Why is that? Maybe there are observations uncertainty for smaller events, or another possibility, different physical process in smaller versus larger events, something that needs to be explored. Switching to a slightly different topic, knowing reconnection flux, can we improve our understanding of flare and CME feedback? Since 2005, we know that there exists this nice correlation between reconnection flux and CME mean velocity. However, most of this past analysis has been done for fairly large CMEs, and it wasn't clear from the timing what is the main driver there, the reconnection or eruption, the CME eruption. Now with SDO, Zhu et al. Performed a very nice analysis where they analyzed 60 slow and fast CMEs using SDO and stereo data. And what they found is indeed for fast CMEs above 600 kilometers, there is this nice correlation between reconnection flux and the CME velocity. However, if you look at slower events, then this nice relationship is gone. Why is that? That's a good question. Another thing that they investigated, Zhu et al. Investigated, is the relationship between the acceleration and the reconnection rate. And they found a nice correlation between the two. Finally, they studied the timing of CME acceleration and reconnection, trying to figure out the chicken and egg problem, what comes first, what drives what. And they found this three population of CMA accelerates first and reconnection happening first, meaning that there is, at least for now, it's impossible to distinguish in between the drivers. Switching to another topic, can we estimate the amount of magnetic flux in the erupting fields? And here we're going to talk about dimmings. What are dimmings? These are gradual darkenings observed in the EUV. They map the foot points of expanding structures, and they are thought to be caused by density decrease as coronal structure isothermally expands. Lately, two types of dimmings have been distinguished: the core dimming due to expansion of pre-existing flux rope, and secondary dimming due to stretching of the overlying arcade. There are a bunch of very nice studies performed on dimmings, individual studies and statistical studies lately, but I want just to mention two of these studies. The statistical study by Dissauer et al. Mentioned earlier did a very nice morphological description, quantitative description of what dimmings are. They've also described some scaling relationship, for example, between dimming properties and the soft X-ray effluence. They also, for the first time, described the properties of the dimming regions in terms of properties of core dimmings and the secondary dimmings. And some of the interesting results that they found is that the flare start time, dimming starts at around the same time as flares. And they also did comparison of ribbon reconnection flux with ribbon dimming fluxes, finding that there is a strong correlation between secondary dimming flux and ribbon flux, meaning that additional reconnection happens, and the two, explaining that the two balance each other. In another study, Dissauer et al. Compared dimmings versus CMEs, and they found that dimmings develop simultaneously with CME onset, and that dimming properties have the highest correlation with CME masses, confirming earlier results. But to sum it all up, dimming's temporal evolution reflects the early CME evolution. And just putting it all in a kind of very simplified eruption scenario, dimming, ribbons, all this business, as pre-existing or in situ form flux rope rises upwards, first we have density drop, and the core dimming is observed in here. Then the reconnection beneath the erupting structures with foot points observed as flare ribbons here feeds additional poloidal flux to the flux rope. And as reconnected field lines that warp this rising flux rope produce increased hoop force, all of these lead to larger CME acceleration and peak velocity. So switching to my last topic, the electric currents. All we know that free magnetic energy is stored in volumetric electric currents in the corona. And the vertical electric currents could be quantified. In the corona, it cannot be quantified because we don't have coronal measurements, but in the photosphere with HMI, we could estimate the vertical electric current from B. And what we learned with HMI is that these currents are highly structured spatially, shown in here. And while currents are balanced over the active region as a whole, they are unbalanced or non-neutralized over each polarity. It has been shown in earlier studies using ground-based observations, but now with HMI, we really have long-term evolution of direct currents and return currents in each polarity shown in here. And we find that these are unbalanced. We also found recently that current neutralization is related to the amount of shear at the polarity inversion line. And both in the simulations and the observations, here is an example of preliminary study that we did where polarity inversion line shear angle is nicely correlated with current non-neutralization within ribbons. And finally, one of the latest results, flare CME productive events have higher non-neutralized currents. And there have been several studies lately looking at 4 to 30 active regions, showing that these the net currents are related to the flare and CME productivity of active regions. So here is my final slide. Using magnetic field measurements from HMI, we learned quite a bit of things about magnetic field changes, Flare reconnected fluxes, dimmings, electric currents. And I'll stop here. Please ask questions. Thank you.
Thank you very much, Masha, for a lovely overview. Do we have any questions in the chat for Masha?
Not that I see any right now, but I guess it's good time for continuing later in the discussion session.
Yeah, I think we've sort of got a few minutes over our session, but I'd just like to thank all four of our wonderful speakers again today for giving a fantastic overview of what STO has taught us over the last 10 years. I think the overarching conclusion is that it's probably raised more questions than it has answered, and which is always a sign of a successful mission. So if people want to take a break for now, I think we're going to split